Welcome everyone. Thank you for attending today's SEL webinar, Communication Basics Part 2. Before we start, I'd like to bring a few items to your attention. This is an audio-only broadcast. All participants are muted. Today's webinar will be 2 hours long, including questions at the end of the presentation. There will be a recording which will be available on our website very soon. If you have any questions throughout the presentation, please submit them to all panelists with the Q&A tool at the bottom right-hand corner of the application. Any questions that are not addressed during the live event will be answered by our presenters via email. We will also be offering PDH credits for participation in today's live event. To receive PDH credits, you must attend at least 75% of the webinar. No partial credits will be awarded. You will receive a certificate via email. My name is Sjaardema. I'm an automation application technologist out of Lakewood, Colorado. Today I will be your first presenter, and our second presenter will be Wellington Oliveira, a communication application engineer out of San Ramon, California. Today's presentation is going to focus on protocols. If you were able to join us yesterday, we covered the media, fiber and serial connections, and Ethernet that these protocols are transmitted over. So what is a protocol? A protocol is a defined set of digital message formats and rules for exchanging data between different computing systems. So this is often for signaling, authenticating data, and detecting. The protocols will define how to detect errors and correct the message and data sent. A common term around protocols is SCADA, supervisory control and data acquisition. Most of these protocols follow a master-slave or client-server relationship. The ones that we'll mainly be covering today are SEL Fast Message, Modbus, and DNP3. In a client and server relationship, the client will send a message to a server requesting information, and that server will respond with the information it has. So the master will perform a poll, the slave will respond, and in this way, the controls are mainly managed by the master. The slave is where all the data is stored. And the master will also do things like sending controls, which the slave will respond to. SEL Fast Message Protocol is one of the primary protocols used by all SEL IEDs. It is supported by every one of our relays. It requires a point-to-point connection, such as RS-232, or a TCP port connection through Ethernet tunneled serial connection. This protocol is a combination of ASCII, which is text that you can see in a terminal, and binary data transfer modes. This allows you to have access through a terminal simultaneous with data transfer of binary information. We also support auto configuration of tag data. This auto configuration will allow a server device to define what tags are available in its memory. SEL Fast Message has two main types of data. There's target data, which is made up of binary relay word bits. These are things like your 52A, your protection trip elements, whether a relay is enabled or not, any data that can be defined as on or off or true or false. This also includes your contact inputs and outputs. Meter data covers the analog values. So this will include data like your voltage, current, frequency, megawatt hours, megawatts, voltamps, and so on. And these are transmitted in floating point format for the majority and phasors for data like voltage and current that have an angle attached to them. In SEL Fast Message Protocol, binary messages allow you to support the receipt of the target and metering data. So these binary messages are transmitted separate from the ASCII messages. The format is defined by the pre-configuration of the index positions. This is what auto configuration controls. So these commands will be sent before a true connection is made between the SEL client and the SEL server. And all tag data are retrieved at the standard pull rate. So if you have your client set to pull once per second, that's the fastest most data will be retrieved. And there will be no timestamp except what's applied at your SEL client. If you want that timestamp data, you can use fast SER. So if it's present in the relay SER settings, timestamps are supported and will be retrieved along with normal target data. SER is the sequential event recorder, and this can be used to create a list of data that you're interested in, an order of operations when things happened. And this data is then transferred on over SEL Fast SER protocol. If you have unsolicited messages coming from the relay, that will also contain the timestamp and the state of the SER target. And Fast SER protocol will also report any SER records until the relay indicates everything has been sent. So it won't wait for a pull. It will simply push the SER data to the controller. So in Fast Message Protocol is the fast operate command. The fast operate will allow you to send commands from a client to a server. So rather than retrieving data, this is actually sending commands, such as the breaker bits, which will trigger the OC or open command and the CC close command targets in relay logic. This is the same as if you were to type open or close into the terminal. In addition to breaker bits, the fast operate protocol allows you to use remote bits, which are typically used for logic. These remote bits, rather than being open and close, use set, clear, or pulse for their logic. If you send a set command, then the bit will be turned on and stay on. Clear is used to undo that latched control, and a pulse will simply turn on and off for a single cycle. Generally, set and clear are used when you want something to stay for a long time, and the pulse command can be used to trigger other logic, such as a cell logic variable, which you could set to have a pickup of 0 cycles and a dropout of 30 cycles. In this case, a single pulse would give you a timer that lasts for 30 cycles. This can be used in conjunction with output contacts, so you could pulse or send a pulse command from your controller or client and have that turn into a 30 cycle closed condition for an output contact. Fast message protocol depends on an auto configuration process to make sure that all data is in the right place every time a client device connects to a server device. The CAS command will give you the configuration data for your event reports. DNAX will give you an index map of the relay word bits. SNS command will give you your SER tag map and index position, pretty much telling the controller where it can get timestamps and the SER information. Those 3 commands are sent over ASCII, but there's also a binary message, the A5C1 fast meter configuration command, that will get the analog meter value names and their index position. If you're ever using a wire capture, you can actually find this A5C1 in the hex data. And you'll also want to look for A5D1, as this will be the fast meter read command, and we'll tell you where your data is coming back from. The data that you are looking for is supported by the relay, but is not supported in fast message protocol natively, you can use a process called flex parsing. Flex parse essentially allows you to type a command that will be sent to the terminal of the relay, and then you can use universal expressions to parse out the data that you're looking for. Commonly, this will look for information such as megawatt hours or megavolt amp hours, as these are not always supported under standard fast message. SEL fast message protocol also allows for something that we call engineering access. This allows you to have a connection through a single serial connection that is transmitting both data to SCADA and also terminal data to an engineer. This is unique to SEL protocol. Modbus and DNP3 don't support anything like this. And in the majority of cases, there is no issue with running both the terminal data and the binary data simultaneously. There is something called a transparent or direct transparent connection for the few cases where you do have issues, such as sending and receiving files through Y modem transfers. In the case that you need to do the transfer like that, you would select a transparent mode for one where you want SCADA data to continue, or a direct transparent mode where you want to pause SCADA data to focus on the terminal session. If you're using a modern connection like the RTAC, this is all managed automatically through the SEL server connection, so you don't have to worry about transparent and direct transparent in most cases. So that was the basics of SEL fast message protocol. It's a pre-configured protocol that gives you that defines all data available in fast message when the client and server connection is first made. There's a lot of overhead with this protocol, but it's very easy to configure, very easy to set up. You just select the tags you want to find. Modbus protocol is a much simpler option. It's one of the most common protocols that you'll see. The most common implementation is referred to as Modbus RTU. This is the pure serial form of Modbus. It was originally developed by Modicon for their PLCs, but these days it's used in many RTUs, PLCs, and other IEDs. It's compatible with EIA 232 and EIA 485 in all their different forms, and there are even variations for native Ethernet applications. Register mapping is defined by a manufacturer. Modbus is, like I mentioned, one of the most common protocols used today. It is very simple for vendors to implement, and it's very low overhead, so it doesn't put a major strain on the hardware being used. So when a register map is defined, it can be either hard-coded into the device if it's simple, or you can have a configurable map option. Boolean data types are stored as single bit registers, so they're just a single bit for on or off, true or false. And holding and input registers are 16-bit, and those can be combined into 32-bit registers as long as your server and client are both capable of understanding that conversion. Four primary ways of storing the data. Your 0x is going to be your discrete outputs, which are coils. These are read-write Boolean values. 1x is going to be a discrete input, which is just a readable value. It can't be written. 3x will be your input registers. This is your analog data that you only want to read, and 4x is a read-write holding register. This is where you can send analog controls or read analog data. To decode a Modbus message, it's actually a very short hex address or hex value that you see here. So our first address is the address of the remote slave IED in blue here. We have the address is 1. Our read holding register operations code is 3. The code is defined in the function codes that you can find in any manual of an SEL product that supports Modbus. After we define which function code we're using, we'll move on to the register address we're starting at. In this case, in green, we say we're starting at 0. And then we'd say how many registers starting from 0 we're going to read. This 0010 is actually 16 because the data is in hexadecimal. And at the end of that, we have a CRC error 16 error detection. This just helps us make sure that nothing got corrupted in transition or in transmission for the message. After receiving this message, the server device will respond. It will respond with its own address, 01 in this case, what type of response it's providing, holding register data, how many bytes it's returning, which in this case is 32 because it's 20 hex. And then it will provide the data, which is contained, or which should be the size of data bytes returned and however many registers it needs to return. And at the end of this, we still have the CRC16 error detection to make sure nothing was lost. Modbus supports 4 primary protocols here. Modbus ASCII is something that we don't see very often these days. Originally, it was supported by a few Modicon devices, a few third-party vendors. The way this worked was it would actually send ASCII text for those hex characters that we were seeing. So it was largely inefficient compared to binary transfer. Modbus RTU just sends the native hex character, or just sends the basic hex characters, your 4-digit or 4-bit values for 0 through F, and it provides all the information over a serial connection. So this is one of the most common. Modbus RTU over TCP is a TCP tunneled serial connection. So this is serial Modbus, but it transmits over an Ethernet network. Modbus TCP is all Ethernet. So everything is managed by TCP ports and IP addresses. There's no conversion back and forth between serial. That is the basics of SEL protocol and Modbus. With that, I'll hand the mic over to Wellington Oliveira. In addition, we'll have time at the end of this. Oh, sorry. Yep. Just a reminder, if you have any questions, feel free to put them in the Q&A section. Thank you, Wellington.
Thank you, Scott. Thank you. Let me share my screen. Hold on a little bit. Okay, so let's go to the next approach of this presentation. This part of the presentation will be about the protocols DNP and mirrorbits protocol. I will be talking about the topology as well in the final of the presentation. And let's start with the DNP protocol. So the DNP protocol, DNP3 is a protocol that defines communication between master stations and slave device with focus on interoperability and reliability. DNP overcomes many limitations of early SCADA systems protocols such as Modbus, and it is an open standard by the DNP user group, and it is free for implementation by any manufacturer. Now the DNP protocol is at IEEE standard number 1815. The DNP is specifically designed to support typical utility SCADA functions such as reading, writing the database over a low bandwidth channel. The DNP also has additional features such as state change report, send events with timestamp, and send the time synchronization to the slave devices. DNP has support to select before execute controls, or SBO, select before operate, the same meaning. And in this SBO, select before operate means before sending a control, the master station sends a message to the slave station to select the digital output or to reserve the digital output. The protocol can be applied to provide communication between RTUs and relays, but also can provide communication between the SCADA systems and RTUs. In the first case, communications between R2 and relays, the R2 will be the master station and the relay will be the slave device. But for SCADA communication between SCADA and R2, the SCADA will be the master and the R2 will be the slave station. So in other words, some devices such R2 can be both master or slave depending on the implementation and settings. Relays are the slave stations only. The DNP3 is an event-based report protocol. And after reading this slide, some customers obviously go to the question, what is an event for the DNP protocol? So, well, for digital inputs, an event is defined as a status change. So, for example, for a status of a circuit breaker, when we have changing the status of a circuit breaker from closed to open, it is a digital input event. For analog inputs, an event is an analog percent change, and the user on the settings defines this percent in a settings called a deadband. The DNP3 also creates the concept of classes. This is a pretty nice feature in the DNP protocol. There are three different classes to allow the master station to send requests and receive a response with only the events in case of the slave station has events on the buffer. This behavior on the DNP protocol avoids consuming bandwidth to transmit data that are not significant to the master station at that time. There are three types of classes available to send events. These classes are Class 1, Class 2, and Class 3. Class 1 has more priority than Class 2, and Class 2 has more priority than Class 3. The DNP protocol also, has one more class called Class 0, but this Class 0 is used by the master station to pull the entire DNP map from the slave, but this class doesn't send any event and doesn't clean the buffer on the slave station. So in other words, the Class 0 on the DNP protocol, it's a little bit similar with the Modbus requests. I will talk later about this. The DNP protocol is an object-based data formatting and doesn't have access to the memory of the device. That's why the DNP introducing the concept of buffer. The standard defines several different types of information, such as binary input, binary output, analog input, analog output, and counters. And each type of information has a different and specific object. And for each object, we also can have different variations. And these variations create subsets in these objects. So for example, for object 30 in the DNP protocol is reserved for analog inputs. In this object 30, we have a variation to send the analog inputs with 16 bits and another one to send an analog inputs with 32 bits. DNP also has support for a float point. It is another variation on the object 30. And the user can consult the object available in the device in the DNP profile document. SEL provides the DNP profile in the instruction manual for each device. So if I open my instruction manual for the relay 751A, I'm able to find the DNP profile on the DNP appendix. I will show a table later with more examples of objects and types of information. Before discussing how the DNP protocol sends the requests, let's remember how protocols such as Modbus sending the polling request. As shown in this slide, in the Modbus protocol, the master station must know the memory region the data points are stored in, or the region map, or the memory register where the data is located, as Scott showed in a couple of slides ago. And in this example, when the master station read a specific region and define how many registers will be reading, the slave respond with all the data in that region. In the DNP protocol, this behavior is a little bit different. The DNP protocol provides the master station and different ways to pulling the information. Could be static pull, or report by exception, and unsolicited report. We are going to talk about these three types of pulling. In the first one, the static pull or integrity pull showed in this slide, the master station sends a class 0 request and receives a response with a complete data map from the slave, with all the binary inputs, all the binary outputs, analog inputs, analog outputs, and counters, everything in the DNP map on the slave station. And in this response, it doesn't come with any event or timestamp. The master station also can send a static pull for a specific object, such as object 30 for analog inputs, and this means the master station can read, for example, only the analog inputs from the slave devices. And, the second way is using reporting by exception. In the reporting by exception, the master sends class 1, 2, and 3 pull, and we receive a response with the slave events, only with the slave events. And this behavior will improve the performance of the communication channel. Typically, the slave will respond with a small packet, depending of the situation. So if the slave station has 3 events to send, will be probably a small packet. But if the slave has, I don't know, 20 or 30 events to send, will be a big packet. And an interesting feature in the DNP protocol is that the slave station can send analog inputs and digital inputs events on the same message. So this means if my master station is pulling class 1, 2, or 3, and the slave station has, for example, after an untrip, the event for one event for the breaker is open and my current is going to 0. So the relay or the slave station will send all these events on the same DNP packet. This is an incredible advantage on the DNP protocol, and this feature improves performance as well. The master station can also combine report by exception, this pulling class 1, 2, and 3, with static pull. In this way, the master can pull frequently for events and sometimes for static data. So, for example, I can set up my RTU, for example, to pulling on relay with class 1, 2, or 3 each 1 or 2 seconds, and set up my integrity pull, my static pull in each 50 minutes, for example. Actually, this is the most common way that customers using the DNP3 protocol in the field. This is combine report by exception pulling and static pulling using class 0. Another way is the unsolicited report by exception. In this way, the slave station can occasionally send events to the master station without a request, and then just waiting for a confirmation for the master station. After receiving this confirmation, the slave station will clean this event from the buffer. But this unsolicited report by exception, it's really recommended for applications with extremely low bandwidth, because in this type of pooling, collisions could happen if you have point to multi-point connections. So keep in mind the recommendation for using unsolicited report by exception is in an extremely low bandwidth connections and in a point-to-point connection. And collisions are caused by 2 or more slaves send events at the same time in a multi-drop connection or point to multi-point. And to get around this problem, the protocol provides the possibility for retransmission unsolicited messages. So we can define this period of retransmission in each slave device. But one more time, keep in mind it's really recommend for low bandwidth applications with point-to-point connection. All right, one more. So the definition of class data. So for new users in the DNP protocol, it's pretty common asking this question: What is class 1, 2, and 3 represent? So what I should set up in my slave device as a class 1, class 2, or class 3? So the answer is basically whatever the slave station defines them as. But typically, all the users, all the DNP users around the world set up the class 1 for binary input events and class 2 for analog input events, and for class 3 counters. But it is possible changing the settings on the slave station. This slide compares the static pool versus event data, and as we can see, the static pool provides the present value it's kind of a snapshot. It's pretty similar when we compare with Modbus protocol. And the response from the slave station doesn't contain timestamp information. And beyond that, it doesn't clean the buffer on the slave station. I like to repeat about this process to not clean the buffer on the relay, because in many cases we saw many problems because customers set up the master station just to pull in the class 0, because using this class 0, the master station is able to get in all the DNP map, and it's pretty easy to set up, right? So, but in this case, when the relay has new events, they are accumulating these events in the buffer. So that's why the recommendation is combine and trying to get in the events from the relays by using unsolicited messages or pulling class 1, 2, or 3. Using this pool, class 1, 2, or 3, the master station will be able to get in the events from the relay as a new value from the slave station, and also could receive the timestamp from the slave station. This slide shows the typically directions of the information. So for binary inputs and analog inputs and counters, is typically information comes from the master station, from the slave station to the master station. And basically the idea is get what's going on at the field, what is the slave station is monitoring. And for binary outputs and analog outputs is typically commands from the master station to the slave station. So it means the break status of the relay I can get from the binary inputs and send binary output to control the breaker, so open or close the breaker. Here is one example of the DNP implementation. So the entire map of the DNP is divided in different types of objects. So we can have binary inputs, binary outputs, analog inputs, analog outputs, and counters. And here is some example of what type of information we can send through the DNP map. So the break status 52A, for example, we can send using the binary inputs object, LEDs, latch functions, SVs, protection alarms. All these Boolean variables can send by the binary outputs. And on the binary outputs, we can send the controls, so open or close the breaker. And the metering is associated with the analog inputs object. So currents, voltage, frequency, all these analog quantities in the analog inputs. The analog outputs could be used to set up points. So for analog outputs, it's not so common for electrical companies. In counters, the master station can pull in the energies, for example, accumulations and analog quantities. And here is one example in how the DNP map can be classified on the slave station. So in this small event, in this small example, we have the break status, the 52A word bit associated with the DNP index 0 for the binary input object, and the TLED 1 in the DNP index 1 for the binary input as well, and same for the TLED 02. But for the analog inputs here, for example, we have currents phase A, B, and C associated with DNP index 0, 1, and 2 in the analog inputs. And here became an interesting point. So we can have the same index number. So I can have index 0 and index 0 for different types of objects. So I can pull in the status of my breaker in the index 0 for binary inputs and send a control to my breaker to open the breaker using the DNP index 0 for the binary output objects. In this example here, we have one index to open the breaker and another index to close the breaker. But it's possible to send the commands open and close the breaker in the same index. I will talk about this later in a couple of slides. So this is the DNP map. So the static data, and the relay also has an event buffer to accumulate all the events. And what happens is when the slave station has a new event, so for example, this digital input index 1 changing from 1 to 0, the slave station will associate this event on the buffer and and accumulate this buffer until sent to the master station. Similar process for the analog inputs, but as I said before, for the analog inputs, an event is a variation greater than the deadband. So, for example, if I set up my slave station here with a deadband for 10 amps, for example, and current is 305, and let's imagine this value changing to 320. So the relay will create an analog event for this analog input index. Similar for counters and how the master station will get in these events. So could be using the pooling class, using class 1, 2, or 3, or the relay send the unsolicited message to the master station. And as I said before, so we can combine the class 1, 2, and 3 pool with the class 0 pool, the static data. The DNP protocol organizes the frames in the data link header transport and application header, and also object header. The first block, this is the first block, the data link header. The message has 2 specific bytes, CRC. CRC means cycle redundancy check, as Scott said before on the Modbus protocol. And it is a technique to detect digital data errors on the communication channel. And one big difference between DNP and Modbus is Modbus has one CRC on the final of the entire message. But in the DNP put 2 bytes for CRC on the first block and 2 more CRC bytes in each 16 bytes. So it means let's imagine this message here is block 0, this one's a block 1, block 2, and block 3. So the CRC, the DNP protocol will include in 2 bytes for CRC for each 16 blocks. And this behavior increasing the protocol's reliability. The data link header on the DNP protocol has a fixed size with 10 bytes and always start with the bytes 0, 5, and 64, always with no exceptions. The next byte is length, So this byte is specific to count the number of bytes of the user in the frame, and the bytes 0, 5, and 64 lang and the CRC are not included in this counting number. The control byte, the DLC, shown in this picture as a DLC, has specific information for the link layer. So, for example, the bit direction defines if the message is a message from the master station to the slave station or an opposite message from the slave station to the master station. The DNP standardized that the messages from the master station to the slave station put this direction bit as logical 1, and messages from the slave station to the master station, this direction bit in this control byte has logical 0. That helps in the troubleshooting. And different from the Modbus protocol, the DNP predicts the address for source station and destination station. So it means if I send a DNP message, for example, from a master station with address DNP address 1 and the slave station with address 5, for example, when the master station sends the request, I will see the destination as number 5 and the source as the number 1. And when the slave station responds, I will see opposite address. So the destination, when the relay responds, the destination will be 1 and the source will be address 5. Additionally, each address has 2 bytes, and this feature 2 bytes allows the an address range of more than 65,000 devices on the same network. For the transport layer, the DNP has just 1 byte, and this 1 byte can control the fragmentation process when the message has more than 255 bytes. And this process is using just two bits in this byte. So there is 2 bits called final and first, and the other 2 bits is used to for sequence number. And this feature is very important, especially for slave station. So let's imagine a response from a master station of a class 0. So the master station sends a class 0, and the slave station will respond this class 0, and this slave station has, for example, 100 binary inputs and 100 analog inputs. So only with these variables, for sure, the DNP will fragment the process in many messages, and this transport byte will control this fragment process. For the next layer, the application header, the DNP protocol predicts a different format for requests and response messages. So for response, when the relay responds a message, the DNP protocol predicts 2 additional bytes for internal indication status. I will show some examples of these internal indications status later. In the object header, is still in the application layer, the stations can define which object will be transmitted and which information will be responded by the slave station. So, for example, when the master station sends a request to the slave station and he wants to read only the analog inputs, for example, so the master station will put what type of object the master station wants to read, and the slave station should respond only with this information. the master station also will define the type of variation. So, for example, when the master station sends a request for slave station to read analog inputs, for example, on object 30, so my master station can define I want to read analog inputs with 16 bits, for example, and the response from the relay should be with this variation with 16 bits. But the standard also provides a way to asking for a default variation. The master station can send a pool, for example, for analog inputs, object 30, and asking for variation 0. This variation 0 means the slave station is free to respond the default variation. And that's why we have on the relay settings the default variation for analog inputs and binary inputs. Still in the application layer, the DNP protocol also has can combine actually the type of object and function code. So function code means what the master station wants to do. The DNP protocol has many function codes, but I put here in this slide only the most common. So function code 01 is reserved to reading function. So when the master station wants to reading analog inputs, for example, the master station will send a function code with 01 and specify the object 30 for analog inputs. If the master station wants to read, for example, binary inputs, object 1, the master station will send a pooling request with function code 01 and object 01. Function code 02 is basically for write function, but is not for send controls. So could be used, for example, to send and write a new timestamp on the relay. And before send this function code 02, typically the master station send this function code 23, the delayed measurement. So this function code 23, it's a way that the master station calculated the latency on the network, and after the relay respond the latency, the master station will send a message with the write. We send a message with the function code write with the correct time, considering this this offset. Function codes 3, 4, and 5 is used for sending controls. Function code 3 and 4 is for select before operate controls. And when the master station sends a select before operate control, the master station first will send a message with this function code 3 to select the digital output, and after the slave station responds to this message, the master will send the operation message with function code 4. But also there is one option to send a direct operate using the function code 05. And in this way, the master station basically send only one message to asking to the slave station to operate in a binary output. The standard also has another one, is 06, is direct operate no ACK. It's in this way the master station send a request to operate the binary output, and the slave station doesn't need to respond to anything, just send the event later. This function code should be used similar like the unsolicited only for communication channels with low bandwidth, because could be more complicated to troubleshooting controls command when we use a direct operation OAC. So when we see a response from the relay for direct operate controls, the slave station can, for example, if my master station sends a direct operate control to the index, I don't know, let's imagine one example, 99, and the relay doesn't have this digital output on the DNP map. So when the relay responds this message, the relay will put a status saying, I don't have support for this DNP index. And this behavior really help us to troubleshooting problems. Other function codes here, for example, 129 and 130 is typically for slave station. So when the master station sends a pulling request for read analog inputs, for example, the slave station will respond with this function code 129 or 81 in hexadecimal and send the objects. When the slave station has unsolicited message to send and the unsolicited is enabled on the relay will send this message with function code 130 or 82 in hexadecimal. Here is a table showing some examples. Let's focus in some types of information. So for binary inputs, the DNP standard reserve the object 1 and object 2. Object 1 is for static binary inputs, and object 2 is for binary input change. So for binary input events to send to the master station. And similarly for analog inputs, we have object 30 for static analog inputs and object 32 for analog inputs events. Regarding the variations, it's like I said before, it's a way to create subsets on the objects. So, for example, for object 1, we have two different variations, variation 1 and variation 2. And variation 1 means the slave station will send only the Boolean status. So if the index is in 0 or in logical 1, that's it, only this. And variation 2 in the object 1 is to provide the slave station to send the quality status for each DNP index. This is very interesting feature to be applied, especially in R2 applications. So, for example, when we have one R2 pulling 25 relays and provide a DNP map to the SCADA system in just one map. When the R2 losing communication with one of the relays, the R2 will change the status of the DNP index associated with that relay that lost communication. It's a pretty interesting way to use especially in R2s. And if we look into more to this table, so we have binary outputs as object 10 and object 12. Object 10 is used just to send to the master station the status of the binary output, if the binary output is closed or open. But when the master station wants to send a control to the slave station, the master station will send a function code with function code, for example, direct operate 05 in object 12. Object 12 means controlling binary outputs. And like I said before, the DNP profile for each device has all the objects supported by the device. Still in this table, we also see other functions such as time synchronization has a specific object. So when the master station wants to send a time synchronization to the slave relay, the master station will send a message with function code 02 write in object 50 for time synchronization. And even the class pooling, class 1, 2, and 3, is also a type of object, is object 60. And the variation defines which type of class is in this object 60. So for example, object 60 variation 1 is class 0, and object 60 variation 2 is a class 1 pooling. And object 60 class variation 3 is a class 2 pooling. The quality attribute or the status flag informs the master station some information such as if the index is in online status, offline, forced, etc. This helps to troubleshoot, especially in applications between communications between SCADA system and R2s. That's why it's really important to set up the, for example, object 1 with the variation that should send the quality attribute. That's really helpful for troubleshooting. The internal indication is another feature that helps a lot to troubleshooting communication issues on DNP applications. Sorry about that. The slave station uses these 2 bytes to send an auto diagnostic to the master station. And the slave station will send important information such as buffer overflow, device trouble, timing synchronization requests, class 1, 2 or 3 available. And typically in the master station, there is an option to respond to these internal indication requests automatically or not. So for example, in our device 3530, we can set up if the AirTag, when the AirTag is a master station, if the master station will respond automatically this internal indication. When we see this internal indication in a communication capture, this really helps a lot for troubleshooting and keeping this in mind. The control relay output block or CROB is used to sending control to the slave station, and it operates based on several parameters, and the user can send the select before operate for security purpose or using a direct operate command. The standard allows different types of commands such as push on, latch off, and triple close. Typically, the push on commands are sent by the master station and using a specific index to do one specific thing. So, for example, if the master station wants to open and close a breaker, open and close the breaker in a relay using push on commands, the master station should send one command to a specific index to open the breaker and another one to close the breaker. But in the DNP protocol, we also have trip close commands. Trip close command is a push command, but with a specific qualifier, and this qualifier will bring it to the slave station if the master station wants to trip or close the output. And these trip and close operations are most common because provide this way to send the same command in the same index. So I can send a push on command trip qualifier to open the breaker and in index 0, for example, and send a push on command with close qualifier on index 0 to close the breaker. Typically, this type of command is the most used in real application, trip and close. But it is possible using the latch on, latch off commands as well. But in this type of way, basically means the master station wants to put the output on the relay in latch on status or latch off. Pulse means just one pulse for a period of time. So here in this slide, we have a summary of the DNP protocol benefits. This protocol have been used for many years ago, and it's pretty common in automation systems. The protocol optimizes the communications, and the user can apply the protocol in a low bandwidth channel, like I said before. There are different types of poolings. The protocol provides different types of objects, and the protocol can be applied using different types of physical connections because it is a protocol with high data integrity based on the CRC. Because the CRC, because the DNP packet could have many CRC bytes, and this is for sure. This is for sure one of the reasons the DNP is used a lot, and we can use in DNP in communication channels with fiber, radios, 232 channel, 485, point-to-point, point-to multi-drop, point-to multi-point, sorry. Okay, now let's talk about mirror bits. So Scott talked about the protocol, SEL protocol and Modbus, and I showed a little bit about the DNP protocol. So these protocols, DNP, Modbus, and SEL protocol is a protocol to provide communication between one R2, for example, and some relays. But the mirror bits protocol is completely different. It's a protocol to provide communication between relays. So the idea here is set up the relays to exchanging information from each other using the mirror bits protocol with a low latency. The mirror bits communication can be applied in a protection pilot schemes, remote device controls, relay cross-stripping, and many other applications. This protocol is available in most modern versions of SEL devices. The customer can using the 232 serial port with DB9 connection, or 232 with a transceiver, or even order relay or a mirror bit device with fiber connection, and even using radio or microwave could be applied for mirror bits protocol. And even by radio or wave, the mirror bits will provide these relays exchange information with low latency. The mirror bits protocol is an asynchronous message to provide two relays to exchange 8 bits of information at high speed in a full duplex communication channel. And like Anthony said yesterday, a full duplex channel means communication in both directions simultaneously. And the Modbus the mirror bits protocol also can provide this high speed for context transfer time. The relay and how works the mirror bits communication. So in this protocol, the relay repeatedly send the status of 8 internal relay elements. So for example, in these 2 relays here, the relay on my left send the 8 bits associated with these word bits TNB1 to TNB8 to the other relay, and the other relay will receive this information and associate in 8 virtual inputs, the RMB1 to RMB8, and these RMBs variables will reflect the status of these TNBs. Same for this side here. So this relay will send the TNBs bits here, and will be received by the other relay in the RMBs variables. Here is one more example showing how the RMB's variables reflect the TMB status. So in this example, this relay number 2, changing the logical status on the TMB1 from 0 to 1. And the other relay, the relay 1, will reflect the status of this logical 1 in the RMB 1. The requirements to using the mirror bits protocol is basically a full duplex communication channel, and because the messages are sent independently in both directions between devices at the same time. And most SEL mirror bits devices support communications of up to 38,400 bits per second on the 232 serial port. For protection schemes, the communication channel should be available during a power system fault, and so the communication channel must be immune to electrical interference caused by fault-generated noise, and that's why typically the connection between the relays is using a non-metallic link. In other words, using fiber. To set up a mirror bits channel is pretty simple. The user needs to set up the serial ports to using the mirror bits protocol and basically choosing between MBA and MB8. So MB have a frame setting with 1 start bit, 6 data bit, and 1 bit for parity and 1 bit for stop bit, and for a total of 9 bits. And the MB8 is a little bit different. The MB8 is designed to send 1 start bit, 8 data bits, no parity, and 1 stop bit for a total of 10 bits. But we can set up 2 devices to communicating, one with MB and another one with MB8. And the way to provide this is just set up the MB device with 2 stop bits, and the communication will match. The letters here, A and B, means the channel A or channel B on the relay. So channel A is the first channel available on the relay, and channel B is the second one. After set up the serial port for using this mirror bit protocol, the user should set up the data rate or the speed, and then set up the address. And this address should be reversed on the application. So, for example, to communicate relay A to relay B, on the relay A, the TX ID, for example, could be 1 and the RX ID 2. And in the relay B, I should put this address in opposite. So TX ID as 2 and RX ID as 1. After sending the settings to the relays and providing the connections, you can using the word bit ROK A for channel A, for the channel A, and ROKB for the channel B, to check if the communication is good or not. And additionally, we can use other protocols such as DNP, Modbus, or SCL protocol to send this information to the SCADA system, because the mirror bit is a protocol to be provided for protection schemes. So it's really important monitoring these word bits at the SCADA system. So if I set up 2 relays in a real substation to become communicating using mirror bits to exchange protection functions, I should set up my SCADA system to pull in these RLK variables and figure out when one of these word bits is in bad status and provide the maintains for the relays. So now let's talk about a little bit about the classic versus modern topologies. So in this example, we have two SEL devices. On my left is SEL 232 device, and on my right is a 3530 AirTag device. So both devices could be used in applications, and I will show a little bit more applications with these devices. So here in this slide, we have 232 in a typical classic topology. In this application, the 232 device is used to provide communication. Is providing a Modbus or DNP interface to the SCADA system or HMI, and pulling relays using SEL protocol. It is possible to integrate some non-SEL devices to the 2032 if this non-SEL device provide a terminal-style interface or a protocol with a very simple data message structure. The 2032 also can receive IDB synchronization from a GPS, for example. And like Anthony showed yesterday, the 2032 can share this IDB synchronization to the relays using the pins 4 and 6 on the DB9 connector on these serial connections. It's a pretty interesting feature in 2032 device. And for modern communications topologies, we can use in the AirTag device. So AirTag device is the new generation of automation controllers for SEL. And this AirTag device can combine serial connections and Ethernet connections on the same topology. So, for example, I can pull in my relays using the serial connections and using the Ethernet connection to connect my AirTag to Ethernet switch. So connecting in our 2730M switch, for example. This specifically about this device, 3530. This device has 3 independent Ethernet ports and up to 33 serial ports. So 33 serial ports. It's a good number of serial ports. But if you have an application with more than 33 serial connections, we can expand this connection using a terminal server such as 3610. So this 3610 will expand the number of the serial connections, and the 3610 will receive in the physical connection from the relays, and I can set up my 3530 to pull in the relay using the IP address of the 3610. So let's imagine I will send a pulling to this relay using the Modbus connection to this relay. So my 3530 will connect into the 3610 using his IP address and a specific TCP port, and on the 3610 settings, I will associating TCP ports with specific serial ports. And the 3610 will remove all the Ethernet header and send only the serial protocol to the relay. And when the relay receives this this message, the 3610 will encapsulate this message and send to the 3530 through the Ethernet network. And also the 3610 can provide time synchronization on the serial ports as well. And the AirTag also can communicate using many types of protocols and could be Modbus R2. Modbus R2 is the serial, as Scott said. Modbus Ethernet, DNP Ethernet, DNP serial, synchrophaser by serial, synchrophaser by Ethernet, and also protocols provided by the standard IEC 61850. So I can pull in relays using 650 MMS or receiving goods messages, an IEC 650 goods message from the relays to my AirTag. And additionally, the customer can using device called 3620. The 3620 could be increasing the security of the substation for cybersecurity purpose and provide firewall functions, router functions, password management, and access control to the relays. So I can set up all my substation to provide remote access, engineer access from engineer access in using protocols such as LDAP and radios. Okay, I think I should pass the microphone again to Scott.
Thank you, Wellington. We've arrived at the Q&A portion of the webinar. Please remember to submit questions to all panelists with the Q&A tool at the bottom right-hand corner of the WebEx application. We do have a few questions to start that have been asked throughout the presentation. So the first one I see here, if telnet is over, if telnet over Ethernet, can you do SEL and DNP protocols at the same time, accessing one IED and reporting to SCADA? Because this is telnet and Ethernet, we actually will have two TCP ports assigned to the connection, and SEL protocol will use one port, DNP protocol will use a separate port, but all of that will be transferred over a single cable. So that was one of the questions that was asked earlier. Let's see, I've got one for Wellington here as well. So Wellington, would you be able to talk about how DNP3 might compare to 61850 MMS performance-wise?
Sure, it's a really interesting question. So the IEC 61850 is standard, and there is many protocols in this standard. So this standard has the concept to having protocols between R2s and relays. This protocol is the MMS, but also has other protocols such as GOOS. GOOS is for provide relays to exchange information. And there is another one called sampled values. So sampled values for provide communication between relays and the process bus. So the process bus is the CT or the PT, the CT or the CT, or merging unit. And talking specifically about the MMS, it's a little bit similar to the DNP. So the concept it's similar. So the idea is provide information from the relay to R2, for example. The MMS protocol has some services like report. So report, it's pretty similar to the unsolicited service in the DNP. It's pretty similar. But the MMS has other features such as the concept of instead to send indexes, the MMS protocol is able to send a tag name to the master station. For example, instead to send a binary input index showing the status of the break status, for example, the MMS has standardization for each type of information. So, for example, break status has a special logical node. So the logical node is XCBR. So protection functions like ANSI function 50, for example, has a special logical node, PIOC. ANSI function 51 has PTOC. So in the MMS protocol, instead to send index, the slave station will send tags names. And to set up the device, the customer should using this tags name to send the file to the relay. The standard also has a way to send a generic logical nodes. But in this case, and I saw many applications and customer using generic objects for the logical node. So if the customer is using generic objects, so it means the customer has the same problem, the DNP. He needs to reading a point list and make sure what is this information. So one of the advantage of the MMS is I can look into the MMS packet and see what means this message. If the relay is sending a break status or current, that is logical nodes to classify the information.
Thank you, Wellington. Got another question here about DNP3. Is deadband set in %? And the answer to that one is it somewhat depends on the device. In most SEL devices, this will be set in engineering units of the point, though. So that's how the deadband is set for DNP3. Another question I got here. The communication from relays to RTAC can be executed with port 4C RS-232, but what protocol is this SEL property? So that port is a generic RS-232 port, which is the protocol will be defined within the relay itself. So you could select SEL protocol, DNP protocol, or Modbus for that port, and all of that will be configurable. That's kind of the difference between what we talked about day one with RS-232 and serial communications, and day two, where we're going over the protocols. Wellington, would you be willing to talk about the what is Modbus RTU over TCP and where would it be used?
Sure. The Modbus R2 is a Modbus implementation for serial channels, and the Modbus TCP is the Modbus implementation to be sent through the Ethernet connections. There is some difference between Modbus R2 and Modbus TCP. So, for example, the Modbus R2 has the CRC bytes for detecting problems on the serial channel. But when we move the communication to the Ethernet network, so the Ethernet standard also has the CRC bytes, right? So what the Modbus standard provide was they changing a little bit the format of the Modbus message. So the Modbus TCP, for example, doesn't have on the Modbus bytes, doesn't have in CRC because the CRC is provided by the Ethernet formatting.
Okay.
So one more thing interesting to say about all this application is sometimes customers be confused with Ethernet applications, but Like Chad explained yesterday, in Ethernet applications, we have the TCP connections, right? And for each TCP number, it's a different service for Ethernet application. So it means, for example, I can use on the Ethernet port on the relay, for example, the IC650 goods message to provide my relay to exchange information to the other relays, and using the DNP protocol on the Ethernet port. So sometimes some customers be confused a little bit about this, because some customers thinking when I move to 650, I should using everything for IC650. Like I should using the GOOS protocol and the MMS protocol, but this is not true. I can using only the GOOS packet, and I can using the DNP protocol on the same Ethernet port. And I also can using both, like you said, Scott, the relay is able to respond to different connections. For example, the Modbus connection and the DNP connection on the same Ethernet port, on the same Ethernet physical port.
Thank you. All right. Got another question here that might see if you I'd ask if you understand this one a bit more than I do. Do you know the full form and use of the CRC, the cyclic redundancy check, in the DNP3 message frame? Or can you repeat how that is used?
So in the DNP protocol, the CRC is used to identify problems on the communication channel, and basically the CRC works as a polynomial that the both master and slave devices know this polynomial, and the master station and the slave station, when transmits this the message, they calculating the CRC and putting this specific position of the bytes and send to the destination device. The destination device will receiving the packet and calculating the CRC as well, and comparing what he received the CRC and what he calculated. So if this calculation is different, so it means the packet, the communication channel is in some problem, and the destination device will discard the packet. And for improving the protocol DNP, so the standard provide 2 CRC bytes in the first block and 2 CRC bytes in each 16 bytes. So it means the DNP protocol is very strong to detect communication problems based on CRC bytes.
Thank you. Next question I've got here. Protocols have pros and cons. Is any one protocol suitable for most applications? We support multiple protocols because each protocol has its specific uses. Modbus is very good for being widely accepted. It's very simple, works the same between many different vendors, and it has a very low bandwidth compared to some other protocols. SEL protocol fits in when you're working with SEL COM processors and SEL relays and other devices that support the protocol, where it's automatically defined. It has your timestamping automatically handled through the SER list, things like that. DNP protocol is kind of the best of both worlds, and why it's largely preferred in the utility world, because it gives you timestamping all your events and it gives you class polling for lower bandwidth. And so it has its own uses. SEL protocol is still probably preferred when you're using SEL relays. Modbus is preferred when nothing else is supported. So there is no one best protocol, but DNP3 is one of the most largely supported between them. Yeah. Taking a look through some of our other questions here. Go. Wellington. Do mirrored bits form the code for SEL protocol, or are these two different?
Hi, Scott. Can you repeat the question?
Sorry about that. So this question is, do mirrored bits form the code for SEL protocol, or are these two different? So are mirrored bits and SEL protocol very similar, or are they completely separate from each other? As they're both SEL proprietary.
So yeah, the mirror bits protocol is protocol provided by SEL, and we can provide the communication between SEL relays or some extension devices such as 3505 using the mirror bits protocol. Yep.
Thank you. There's an interesting one about how to choose what type of commands you're sending from DNP3. So Wellington, regarding commands such as pulse on off, pulse with qualifier, and latch commands, when would you choose to use a latch command? Why would you use a latch compared to a pulse command? And typically, pulse commands are preferred, correct?
Yeah, that's correct. So typically, the pulse-on command is preferred because the idea of the pulse is just provide a small pulse on the digital output, and this concept comes from the communications between SCADA system and legacy R2s. So these legacy R2s was connected to directly to the breaker. So basically, the concept of these type of commands, latch on, latch off, pulse-on, was based on this concept of R2s. But even today, the pulse-on command is preferred, and especially the trip close command, because we can use the same digital output index to send the control and send the contra control. So I mean, send the open the breaker and send the close the breaker, or send a command to block one function on the relay and to enable the function again. So that's why pulse command is more common in DNP applications. So I saw another interesting question here. Can Mirror-bits support 3 points, 3 connections, three point-to-point connections? So sometimes, especially in old applications, sometimes customer needs to share information from one relay to many relays. And for example, let's imagine we need to share this information from one relay to 5 relays. So the relay doesn't have 5 serial ports. And based on this, SEL developed a special device for this. It's a 2100 device. And this 2100 device can concentrate all the Mirror-bits connections and processing the Mirror-bits receiving from one relay and send to the other relays. So it's another way to create Mirror-bits topology, share information to many relays using this 2100 device. Today, some customer is moving to 62850 based on Ethernet connections, but there is many concerns on the market because could be increasing the cybersecurity risk, right? So there is these 2 points. So IC650 Goose Message can provide an easy way to share information between relays, but increasing the cybersecurity risk. And on the other hand, Mirror-bits is pretty fast, but has this limitation of the number of serial ports.
All right. Just got another question that came in. The question was, could I just use one communication protocol, or do I need to use various protocols because of the design of SEL devices? The answer to that is, if one protocol meets all your needs, then one protocol is all you need. If DNP3 and the timestamping is all you need, as you're just looking for historical data, then there's no need to dig into anything else. But if for some case you need both the historical data of all your analogs, but you also want protection speed from something like mirrored bits, then that would be a case where you need to use 2 different protocols because they have completely different pros and cons, and neither one can meet the most powerful functions of the other. So in most cases, one protocol is enough, but there will be times when you'll need both or multiples.
Right. So I got another question here. So how to minimize buffer overflow problems? And should one separate input into different classes? Are buffer overflows due to assigning all points in the class 0? So basically, in these new devices, we have a device with more memory. So it is not common to see buffer overflow problems as long as you have class 1 pulleys on the master station. But like I said, sometimes a few customers set up the master station to pull only the class 0 because it's simple. It's pretty simple to set up only one pull and send this pull to the slave station. So in situations like this with only class 0, for sure, you will see buffer overflow in the internal indication bytes on the DNP message sometime later.
All right. I know we're not really covering 61850 in this presentation, but you're very knowledgeable about it, Wellington. How does the speed of mirrored bits compare to goose messaging for protection applications such as transfer tripping?
So that is a very good. This is a good question. So mirror bits latency between two different relays. We can set up a test or using the sequence of events on the relay to verify the latency. But depends of the speed on each on the serial port settings, but typically is around 4 milliseconds, something like this. Maybe a little bit less, maybe a little bit more. The IC650 Goose, there is a strict requirement for the latency in the local area network should be 3 milliseconds or less between two different relays. So if I send a Goose message from relay A to relay B, this Goose message should receive in the relay B in 3 milliseconds or less. And the same thing we can calculating this using the sequence of event on the relay, or sometimes some customers to validating the IC650 protocol. Typically, they creating ping pong test. So one relay send the Goose packet to another relay. This second relay subscribe the Goose message, and then send the Goose message again. So in my first relay, I can compare the time that I received the Goose message from the relay B, and with the time that I send the Goose event. And for sure, I need to consider the cycle time on the relay B. So, but typically, it's pretty similar. The mirror bits latency with the Goose latency.
Okay. So a question that just came in. If there are multiple protocols managed by the RTAC RTU, and there is a failure in a device that does not have SEL protocol, how will the faulty device be identified having issues? The RTAC is actually aware on multiple protocols of whether it's online or offline. The way it finds this information is a little bit different between protocols. SEL protocol, many of the protocols will have a timeout. Some of them will actually use TCP connections to say whether it's online or offline. So each protocol has its own way of notifying. If you have multiple connections, like a DNP connection to a device and an SEL protocol connection to a device, that then those could actually monitor each other unless both go down in a case like the device powering off. But if you're asking about if there is a failure in a device that doesn't have SEL protocol, how will it be identified? SEL protocol identifies one way. DNP protocol will also identify itself using those offline bits. So the offline bit is contained within the RTAC's POU pin settings for each device. All right. It seems like the questions have slowed down quite a bit. So thank you for all the questions you asked. We've now reached the end of the Q&A portion. If your question was not answered live, you'll receive an answer via email directly from one of the presenters. We hope you've enjoyed today's SEL webinar. And to learn more about this topic, please visit our website. Have a wonderful day.